Good morning, everyone. It's an honor to be here at the ACI. I'm Sudharsan. I'm a master's student at UFI. I work with Professor Nishant Garg. The topic that I'll be presenting today is on moving towards low-clinker limestone calcined clay cement, insights on carbonation performance. The title is a mouthful, but we'll try to break it down in the course of time. So we started off 20, 30 years ago with 10 to 30% cement replacement. A decade ago, we reached 50% cement replacement with LC350. Now the goal is to go towards greater than 50% cement replacement, and that is the point of the study today. Why are we interested in this? The point is we are at a critical stage in time where if we do not act fast, we will see really catastrophic change in temperature. So this graph is about the change in the global mean surface temperature versus time. And if we continue business as usual, we'll reach somewhere plus 7 degrees Celsius in 2100. So when I'll be 100 years old, we will not have a planet to live in. So that is why every activity that we work on should focus on decarbonization. A decline in the availability of SCMs, conventional SCMs, especially fly ash and slag, necessitate that we move towards different or low clinker supplementary cementitious materials. In this case, we have calcined clay and limestone, which are abundant in regions where construction demand is rising, especially in regions in Asia and regions of Africa. So that is why LC3 has been a very attractive alternate to OPC with similar, if not better, performance in mechanical and durability perspective. So comparing OPC and LC350, we have about 50% replacement of cement with calcined clay and limestone. The question is, can we go towards lower clinker contents? By that we mean, can we go towards LC335 and LC325 with about 25 and 35% clinker? So in this curve, you see the global warming potential, and we have 4 different kinds of mixes, OPC through LC325. We definitely see that there is a decrease in the global warming potential comparing OPC, but the biggest jump is from OPC to LC350. There is a dilution factor here that should be taken into account. So we are trying to figure out what else are the challenges that these low clinker blends contain. And one of the biggest challenge is its carbonation resistance. In this curve, we see the reduction in the global warming potential on the y-axis and the carbonation coefficient or the carbonation rate, typically in units of millimeters per root of time, normalized to OPC. So as we reduce the global warming potential, which means we are either reducing clinker or we are building more sustainable blends, we are going right on the curve, which is we are increasing the carbonation coefficient. Similarly, if we continue to replace clinker, we have a curve that increases the carbonation coefficient. This is not desirable for various reasons. Our solution to this approach is depicted in this slide. We add a certain amount of portlandite in the starting mix to enhance the buffer capacity of our low clinker LC3. So this is an LC335, traditional LC335 blend with 35% clinker, and the rest is calcined clay, limestone, and gypsum. Our new blend is LC335 plus a little bit of portlandite, which is given in this picture. So we have the same clinker content, but we are adding about 10% of portlandite in the starting mix. What we see here are 2 SEM micrographs with its EDX map. What we see here is in the bottom curve with the EDX data, we see a cluster of stratalingite AFM phase, which is depicted in this box. The reason we have stratalingite is the increased degree of reaction of the metakaolin with this added amount of portlandite, which causes a refinement of the porosity, and that also enhances its buffer capacity. So with that in mind, we tended to reduce the amount of portlandite because portlandite also has a CO2 footprint. With new sets of blends with 1, 3, and 5% portlandite addition, we definitely see a decrease in the depth of carbonation. So this is natural carbonation data. We see a decrease in the depth of carbonation with time. We also see a plateauing of the depth values with time. So we hypothesized that this decrease in depth and the plateauing of the depth data is caused by the refinement of the microstructure, which inhibits the ingress of CO2. Now we see a curve that shows the decline or the decrease in the carbonation coefficient as you increase the portlandite content, comparing natural and accelerated carbonation. So we see a correlation which is similar to the natural carbonation, but about 30% reduction in the depth, in the carbonation rate, which is caused by the decreased depth. Now, this data is about 3 years of natural carbonation, so really long-term data, compared to OPC. So OPC fares really well in natural carbonation because of its enhanced buffer capacity, high amounts of reactive lime in it. LC335 and LC325 are very high depths of carbonation compared to OPC because of its reduced clinker contents. With a certain amount of portlandite added to it, we reduce the amount of depth that we have in these graphs. Now, to just focus on these LC3 blends, we have to understand how much it has reduced. So for the LC335 with portlandite, we have about 45% reduction in the depth of carbonation. Similarly, for the LC325, we have an even greater substantial reduction in the depth with about 64% reduction. So to conclude, we have defined that LC335 and low clinker contents is possible, but we definitely have to look at its carbonation resistance. Our solution involves adding a certain amount of portlandite to an LC335 system to enhance its buffer capacity by 2 ways. One is we enhance its buffer, and second, we also refine its microstructure so that we inhibit CO2 to ingress with time. Finally, realistic carbonation exposures are important to consider with these low clinker systems because accelerated carbonation might not be the most accurate way of depicting its carbonation resistance. So the ideal outcome here would be to use low clinker systems in reinforced concrete, and this research is one step at least to make us understand the possibility of using low clinker systems in reinforced concrete applications. With that, I would like to thank the team. This is a collaborative effort with EPFL in Switzerland and UFI. So part of this work was done in EPFL through the Think Swiss Fellowship. So if people are interested to go to Switzerland, Think Swiss is an amazing opportunity. With that, I'm happy to take questions. Thank you so much for your time.